Why do atomic energy shells have negative energy values? It seems quite counterintuitive because energy is typically thought of as a positive quantity. Mathematically speaking, this makes perfect sense, because the equation we use to model atomic shell energy can only churn out negative numbers. From a conceptual standpoint, however, things are a bit more complicated. It's helpful to quantify shell energy with respect to the electrons which occupy them. And in so doing, electrons take on the energy of the shells they occupy. So if an electron occupies the second shell, for instance, it's going to have exactly the amount of energy associated with the n equals 2 shell, negative 5.45 times 10 to the negative 19 joules. Now let's take the limit of this equation as n approaches infinity. In other words, we plug in larger and larger and larger values of n until the energy values we churn out are so close to zero, but still negative, that it essentially gets to zero. This is what's called the infinity shell. It has zero energy, and thus if our electron occupies this theoretical shell, the electron will also have zero energy. Now, the infinity shell is not an actual shell possessed by the atom, because infinity is not a tangible number that n can be. Here's another way of visualizing it, where our electron is at the cusp of our atom. So there's no actual connection with the nucleus, but our electron also doesn't wander off. It's just kind of there. So from this infinity shell, we go from no bond to the electron coming into our atom and forming a bond with the nucleus. Specifically, the proton and electron form a stabilizing electrostatic attraction, a chemical bond. And when attractive chemical bonds form, energy is lost in the process. Thus, the energy of this electron will decrease, so it gets more negative. So if our electron started out at zero energy and then it proceeds to lose energy, it will by definition have a negative energy. And this is the case for each one of these shells. With that said, how much energy is lost in the formation of a bond with the electron occupying the n equals 2 shell? Now, it is true that the energy of the shell is negative 5.45 times 10 to the negative 19 joules. But that means that a positive 5.45 times 10 to the negative 19 joules was lost from the system for the electron to go from zero to the negative version. As a point of clarification, the change in energy to form this bond is negative, but it's more conceptually intuitive and thorough to say that a positive amount of energy was lost from the system. Analogously, my change in money was negative $5 versus I spent $5. I'm $5 in debt either way if I started with zero in my bank account. Consequently, if I owed $5, I would need to gain $5 to break the bond of my debt. Thus, in order to break this bond, we would need to add the same amount of energy that we are in debt with. Here's a more holistic way of viewing it. For each shell, the amount of energy required to break the bond and the energy of the shell, of the electron, are equal and opposite. This one's positive, this one's negative. The lower the n value, the larger the energy deficit and consequently energy required to break that bond, as in we would have to add in energy to get the electron back to 0 joules of energy. As you can see, the strength or stability of the bond holding the electron to the nucleus is directly proportional to the amount of energy required to break the bond. Likewise, the larger the negative our electron energy is, i.e. the lower n values, the stronger the bond is with the nucleus, as opposed to weaker bonds associated with small negative energies.